So this is problem 57 from chapter 28. 57. Here we have a very large, flat, non-conducting sheet of thickness T that carries a uniform current density J throughout, and determine the magnetic field, magnetic interaction, the distance y above the plane. So let me first make a drawing, just to illustrate what's going on here. So we have some infinite sheet of thickness T, and this is carrying some current, some current density of J throughout, and we are looking at a point P, point P that is of distance y from this plane, and we are asked the magnetic field at this point. Okay, so what's the magnetic field at the point P? P. Okay. Now, at first, this looks like it's going to be very nasty, but we can actually utilize Ampere's law for this problem because it has a very high degree of symmetry. Okay? So this has translational symmetry in this direction and translational symmetry in this direction. Okay? It's not homogeneous and isotropic, so it's one of those systems that's not isotropic. It has a preferred direction, but it's completely homogeneous. Wherever you go on the plane, it is the same, but there is a preferred direction in the plane. Different directions are not identical to each other, but different locations are identical to each other. Okay? So we are going to be able to utilize Ampere's law, but before we actually utilize Ampere's law, we actually need to figure out what the magnetic field looks like, and then we can determine its magnitude. So let's look at this from one side. I'm going to look at this from front. So my J is now coming towards me, and I'm going to choose some point P over here, and let's look at the influence of one little segment of current that produces a magnetic field at this point P. Okay? So this is going to this is now like an infinite line of current, and I know what its magnetic field looks like. It looks like a circle, so this is going to be something that connects these two, and it's going to be perpendicular to that line. Okay? I have been using blue for magnetic field, so I'll just stick to that. So this is the magnetic field. Let's call this segment 1. This is going to be just B1, and there is a corresponding symmetrical counterpart to this that is going to look like this. So if I connect these two, now this is of course horrible drawing because this looks like it's the extension of that one. It's not necessarily so. Okay? So, but this is going to produce a magnetic field. So if I call this segment 2, this is going to produce a magnetic field this way. Now the point of this is that for every line of current that you pick from here, you can choose a corresponding line of current over there, and for the upper part of this sheet of current, the horizontal components of these magnetic fields are going to cancel. Okay? So I'm going to get a resultant magnetic field this way, and I can do this for any pair on two sides of this point. Right? So which means that on top of the sheet, all the magnetic field is going to be to the left. Now, by the same argument, the magnetic field at the bottom, at the lower part, is going to be to the right. Right. So this is going to produce the magnetic field that's produced by this one is now going to be in this direction. The magnetic field produced by this one is now going to be in this direction, okay, and they're going to lead to a resultant magnetic field this way. Okay. Now, once I know that the direction of the magnetic field is in this fashion, then I can actually draw an Amperian loop and apply Ampere's law. Okay, so I'm going to pick up a different color of chalk, and the loop I choose to draw is going to look like this. Okay? And I'm going to choose the orientation of the loop so it actually agrees with the magnetic field on both sides. Right? So let's call the length of this loop some L, and its distance is going to be, doesn't really matter, but just y on this side and y on this side. So 2y plus t in total. It doesn't really matter. Okay. So what I need is applying Ampere's law to this system. I can now get rid of this. I no longer need it. And Ampere's law tells me that P dot dl is just going to be mu naught times current enclosed. So over this part, the vertical parts of the loop, this dot product is going to vanish because the magnetic field is horizontal. The dl element on those parts is vertical. The dot product of two orthogonal vectors, two perpendicular vectors, is just 0. So those parts vanish. For this part and that part, it becomes a simple product because they are in the same direction. Okay? And I can easily take the integral over here. B is just constant. So first let's do this. Okay, let's call these segments 1 and 2. So this becomes an integral over 1 b dl plus an integral over 2 b dl. These b's can be taken out because they are constant. Yeah, and then this is just the length. Okay, so this is just L, this is just L, so this becomes 2BL. Now, we need to evaluate the right-hand side, so this is just mu naught times the current enclosed. Well, the current enclosed will be the surface area over here times the current density, okay, and that is just going to be L times T times just J. Okay. And as you will expect, the L's cancel because that was our hypothetical loop. The answer should not depend on what we chose as the size of our loop. And it's also independent of y. The y never shows up, but the b is going to be mu naught t j over 2. Okay. That seems to be the case. And even though this looks formidable at first, that you need to do some integral and so on and so forth, because the problem has a very high degree of symmetry, we can utilize Ampere's law. This is very rare. This is very, very rare. Just like Gauss's law, you need a very high degree of symmetry to apply Ampere's law. But before you do that, you need to figure out the direction of the magnetic field. Okay? And that can be done, again, by using symmetry. And once you do that, then you can take these integrals very easily, and you can actually apply Ampere's law and evaluate B for this problem.